All right. Looking at the zonal mean meridional sections now going all the way to the poles for temperature and specific humidity. The contours here are the specific humidities, and those are in 10 to the minus 3 kilogram per kilogram as contours, and the colors are the temperatures, of course, ranging from over 30 degrees to minus less than minus 80 degrees, with the minus 60 degree isotherm being shown in these white contours. These data are produced from what are called reanalysis. In this case, the NOAA's National Center for Environmental Prediction Center reanalysis. Reanalyses are basically, in case you don't already know, are the merging of observations and models. So when you go back in time, you don't always have full coverage in time and space for the various essential variables you need for studying these processes. And models are not always perfect, but there are methodologies, technologies called data assimilation, where knowing the error structures of the model and the data and how to blend them together, you can produce these reanalyses. There are many details. Obviously, I won't go into these, but you can read up. And I think I have a podcast in the other course on a little bit more detail. Okay, so what do we see here? Again, you're looking at June, July, August, and December, January, February. Just like you saw in the sea surface temperature plot, which again we'll come back to later on. If you look at the red colors, the warmest temperatures, they are spread more into the northern hemisphere when the sun is in the northern hemisphere, as you can expect, and it sloshes back in the atmosphere towards the southern hemisphere. And the atmosphere, gets mighty cold as you go up into the atmosphere towards the ceiling of the troposphere, we call tropopause. And as we saw in sea surface temperature, the coldest temperatures here are actually in the winter hemisphere and in the upper atmosphere in the low latitudes. We will see dynamically that when there is heating at the surface, evaporation, rising motion, and condensational heating drives further rising and cloud formation and deep convective clouds, the cloud top temperatures get very cold, and that's why you end up with these temperatures less than minus 60 degrees centigrade. That's really cold, right? So you can clearly see the asymmetry also in terms of the surface level temperatures here at 90 north in the summer versus the southern hemisphere summer. There are significant differences in the minimum temperatures during the winters. The specific humidities clearly high in the low latitudes and at closer to the surface, drop off as you go into the upper atmosphere, because even though evaporation and rising air is taking the humidity water vapor with it, it rains out and quickly dries out, so the upper atmosphere basically has no humidity, and higher latitudes have no humidity either. And again, you can clearly see the slight difference or asymmetry in the specific humidity also at the polar latitudes beyond let's say 70 north and 70 south here. Much drier with Antarctica and Southern Ocean. Southern Ocean is special. We will see that, especially because when you have global warming going on, the Southern Ocean's role becomes even more significantly asymmetric compared to the Northern Hemisphere, because it's a channel, whereas the Northern Hemisphere has land distribution, which makes a big difference in terms of how much wind energy you can put into the ocean, and so on. So we'll look at all sorts of details later on. The next figure will show zonally average precipitation between, again, pole to pole for June, July, August, September, October, November, DJF and MAM. So you can get used to these terminologies. Here we are with the solstitial seasons of JJA and DJF, and equinoctial seasons of SON and MAM, where the equatorial crossing of the sun happens and we get what are called equinoxes, or equal day and night at all latitudes when sun is on the equator. So average rain rate is typically done in millimeter per day. Peter also provides figures of total precipitation by volume in meter cube per day. Preparing these notes takes a long time, so I will apologize ahead of time for not doing these as subscripts and superscripts and so on, but I hope you can live with that for the sake of helping me do these without spending a whole lot of time on those little things. Well, it's important, but I just didn't do it. Okay, so distributions are shown for the annual average and then the seasons, and then results will be summarized in table 2.1, as we will see in the next chapter when we look at hydrology and heat exchanges. These are precipitation data sets from Global Precipitation Climatology Project, and calculations using more latitudinally constrained CMORPH dataset, which would yield very similar results. It depends on the satellite that's making the measurements. There are compromises to be made in the spatial resolution, temporal resolution, and the latitudinal coverage of these satellites. That's where those differences in the data products come from. GPCP combines all the gauge data and other radar data and satellite data and so on and so forth. Okay, so this is a bit detailed, so don't worry, we'll go through it. What is being shown? Rainfall rate in millimeter per day. So for all seasons, and then for ocean and land, and then volume of rain 10 to the 10 meter cube per day, and annual volume. So instead of the seasonal volume, you look at the annual volume, and you will see that broadly speaking the hemispheric asymmetries are still visible down here, but as you go to higher latitudes there are those higher latitude tropical storm bands which produce rain. So let's start here. You can see MAM, the equinoctial season, and SON are not perfectly symmetric. So SON, it's hard to see the color, and JJA are very similar in the northern hemisphere and in slightly different in the southern hemisphere. DJF, you can see that the ITCZ, which we haven't defined yet, the region where large-scale convergence happens and a lot of rainfall happens with the peak, has shifted. So sun is in the north, maximum rainfall is in the north. Sun is in the south, maximum rainfall is in the south. You can see the drop off here, so you will see the broad bands of secondary maxima in these sections of rains are seen at mid latitudes, where we will see the storm track dynamics. Of course, that's beyond the tropics, so we will just look at it in terms of extratropical forcing of the tropics and tropical interactions with the extratropics and so on. When you look at the ocean rain, the JJA and SON are almost identical. Obviously they are different for the land. That's where this land plus ocean difference comes from. And again, the seasonality, you can see now the seasonality when you do land plus ocean is not so obvious, but here much more spread out. So land has much less of a seasonality and has a sharper peak than the ocean in terms of the distribution of rain over these latitudes beyond the Hadley cell. So those who already know what a Hadley cell is, you know what I mean. But the mid-latitude rain here, much more widespread, and you can see the land distribution is very different in the southern hemisphere than in the northern hemisphere, so you see that difference there as well. I won't spend too much time on the volume of rain, but it does tell you that since Earth is a sphere and the area drops off as you go towards higher latitudes, right? The smaller circumference, smaller area. You have to be aware that the rain rates by themselves will be very different for higher latitudes and lower latitudes because of this Mercator projection or the area reduction over the sphere as you go towards higher latitudes. What else can I say? You can see the difference in rain rates and volume of rain remarkably different here on land. And land plus ocean, hemispheric rainfall is almost the same. So when you think of the monsoons in the northern hemisphere and massive amounts of water vapor being moved across the equator for the monsoons, and then the land being less so in the southern hemisphere, it turns out that the hemispheric amount of rain is really not that different when you look at the annual volumes. Oceanic rain, of course, there's a difference because the northern hemisphere has much more land than the southern hemisphere. More ocean in the southern hemisphere, especially the Southern Ocean. And land also, obviously, volume-wise would have much different rain. You can see the long distribution here compared to the southern hemisphere. So these are simple features, but if you're going to get into this field, then it's better for you to know these climatologies like the back of your hand. You should just be in your head, especially the key features that you may focus on, whether it's the Indian monsoon, East Asian monsoon, or West Africa, and so on and so forth. So you should just be able to pull them up in your head by memory.